volunteer?
Yeah.
Wow, that's amazing. That's so nice.
I didn't know his last name at first, so I didn't realize it was him. So I was like, is it a parent? So I was looking at the name, and I'm like, Bill Ezekiel. And I'm like, oh.
That's so nice.
So then the thing corrected me, and I'm like, oh, it's one of our volunteers. That's super nice.
That's nice.
Yeah.
Maybe I'll bring it in here and put it here.
Although it's going to cover all the beautiful faces, but you could set it there. Do you want me to bring it in?
Yeah, let's bring it in.
Good, where are you? Hey, Jeremy.
All right, everyone, we're going to get started now. Okay, so welcome, friends and family, to our Nanoscience Lab B 2024 final presentations here at the California Nanosystems Institute at UCLA. My name is Dr. Shailene Tanimoto. I'm the education manager here at CNSI, and I've had the privilege of being with your students over the last week, watching them learn and grow. And so we're very excited today to show you all that they've learned. So first, I'd like to start us off by welcoming you all to UCLA. UCLA was founded in 1919. We are the second oldest school in the UC system, and our campus spans 419 acres, so we're a very big campus. UCLA boasts 337 undergraduate and graduate degree programs with 31,600 undergraduate students, 10% of which are international students, 31% are first-generation students, and 42%, or about 13,500 of those undergraduates, major in the life sciences and physical sciences. And then we are here today at the California Nanosystems Institute, or the CNSI at UCLA. We are one of Governor Gray Davis's Institutes for Science Innovation. And we were initially established in 2001 as an engine for innovation based on the belief that the defining technologies of the 21st century will arise from understanding and constructing functional nanosystems through controlled integration of nanoscale components. So why do we care about the nanoscale and how small is nano? You'll be hearing a lot from your students today about why the nanoscale is interesting to us. But I wanted to give you, the audience, some context on how small nano is. So to help us visualize this, I want you to think about a nano-sized object like a virus. Viruses, like this one, for example, is about 28 nanometers in diameter. And if you think about the number of virus particles that could coat the surface of a standard size American football, that's equivalent to the number of footballs that could coat the surface of the Earth, okay? So nano is really, really small, and interesting physics and chemistry happens at this scale, and it has far-ranging impacts on a variety of fields, including physics, chemistry, engineering, and biology. And so the CNSI at UCLA, we are a department here, but we're not a degree-granting department. Instead, we are this interdisciplinary hub for research, technology, education, and entrepreneurship. Our education team is composed of Professor Sarah Tolbert, Dr. Rita Blake, here in the front row, me, Dr. Shailene Tanimoto, and Dr. Elaine Morita, our program coordinator. And so throughout the year, we run various programs, including professional development workshops for teachers. So the same experiments that your students perform this week, we teach teachers those experiments, and we give them a free kit of supplies so they can take that back to their classrooms. And that's what we do mostly through the academic year. We also have a Nanovation competition for 6th through 12th graders that combines nanoscience and entrepreneurship. We do public outreach events in our local area. And then what you all are here for are our summer sessions, programs for high school students. So Nanoscience Lab is a one-week summer program for rising sophomores through graduating senior high school students from around the world. We had 36 students enrolled in our summer 2024 class, 20 of which lived up in the dorms and 16 of which were commuter students. So in the morning, you can see that the Sorry, clicking the wrong button here. In the morning, the students performed a different nanoscience experiment each day. And then in the afternoon, they heard a guest speaker. And then following that, they had these science-themed afternoon activities. And so I was taking some pictures throughout the week of our students, and I will share all nearly 100 pictures that I've taken throughout the week. So parents, you will get this, and I'm sure your student is in at least one of them. But you can see we were in the lobby. Students were able to don lab coats, gloves, safety goggles, and perform these experiments out in the lobby. And then they heard some amazing guest lectures from Professor Sarah Tolbert, Professor Jose Rodriguez, Professor Ben Schwartz, Dr. Paloma Castro, and then a graduate student, Alyssa Arnheim. And your students participated amazingly. They asked really great questions, not just about the science, but also about how these guest lecturers made it to where they are in science. So what was their journey? What went into their decision-making process? So we had some really great questions and participations from our students this week. And then lastly, we had these science-themed afternoon activities. They always related back to the experiment that the students performed in the morning. Sometimes they were guest lectures that they heard right here in the auditorium. Some of it was performing additional experiments, and some of it was testing solar cells outside in the sunlight. So hopefully these enriched the experience that they had with the experiments that they performed in the morning. And so one of the key things that we wanted your students to learn are our skills in science, because we are a science class. So these are things related to nanoscience. So how small is nano? Why is the nanoscale interesting? And how does nanoscience appear in our everyday lives? And also about being a scientist. So what does it mean to be a scientist? How do scientists design and perform experiments? And what tools do scientists use? But beyond that, and because we know not all of your students will go on to be scientists, we want to teach them some skills in life as well. And so really key to all of this is the growth mindset. And this is the belief a person has that they can learn more or be good at anything if they work hard and persevere. And let me tell you, your kids, they worked hard and they persevered this week. It was a very challenging course, but we are so very proud of all that they achieved. So other things that we wanted them to learn are critical thinking, communication, collaboration, teamwork and empathy, creativity, curiosity, problem solving, and introspection. And so your students participated in these activities, these reflection activities that I had them do each day. So they would write their name and some reflection on these Post-it notes, and our lovely resident assistants arranged them in a beautiful CNSI pattern here along our windows. So these are right outside in the lobby on the windows, so if you want to go around and read some of these reflections that your students had, please feel free to do so. Okay, so a lot of amazing people made this whole course happen, and we just like to take a moment at the top to thank a lot of these people. So first of all, we have our Nanoscience Lab instructors. These are UCLA graduate students in STEM disciplines, and various of them worked with us throughout the week to help teach your students these nanoscience experiments. So let's take a moment to thank our instructors. Next, we have our resident assistants, so Kylie and Emma. They lived in the dorms with 20 high school students this week. Yeah, they did that. We are very thankful for them, and they are very amazing people. I'd also just like to take a moment, you'll see here, they are in cap and gown. That is because they are graduates of UCLA, class of 2024. So we're very proud of them for that. But extra special today is that they've been our lab assistants for a while. Oh man, I told myself I wouldn't cry. Okay, they're leaving us next week to go on and do amazing things. And we're gonna miss them so much. So I just wanna do an extra big thank you for all their years that they've helped us with this program. So thank you guys. Okay, and then we have to thank our guest lecturers. So again, Professor Rodriguez, Professor Shorts, Dr. Paloma Castellera Costa, and Alyssa Arnheim. Again, they shared their science research with us, which is amazing. It's all related to nanoscience. But then they also shared with us their journeys from high school to where they are now and what influenced their decisions on how they got there. And so I hope that some of your students take away some key information from them and it helps to inform you about some decisions that you guys are going to make in the future. So thank you to our guest lecturers. And then this year we had a couple experiments that were new to this program. Our solar cell activities, our solar cells experiment and our biosensors experiment. We haven't done them for this class before, so we had to develop some afternoon activities that would pair nicely with these experiments. And so I just want to thank these instructors that helped us to develop those experiments. All right, and lastly, we have all of our CNSI staff, our technology center staff, our events staff. All of these amazing people help to make it happen. So our lunches every day, the audio visual happening, the tours that you all went on, these are thanks to the CNSI staff. So thank you guys. Okay. So now it's time for the main event. So the goals of our class were to expose students to advanced topics in nanoscience and also to develop some life skills and skills in science communication. So every night this week, the students were tasked with a homework assignment in which they had to draw a picture analogy to explain the essence of a nanoscience concept that was covered in class. So they could not literally draw what they did, but they had to represent what they did through everyday scenes or topics or encounters so that it would be familiar to someone who knows nothing about science. So if this sounds very hard, that's because it is very hard, okay? So we asked them to do this really challenging task, and they rose to the challenge, okay? So we will be featuring some artwork from some of our students this week, and other groups will have to interpret and present on that image that another student drew. And they'll talk about how they might improve this analogy. So what's key to science communication and communicating science in non-science ways with these picture analogies is that no analogy is going to be perfect. There will be limitations to each analogy because you cannot fully capture all of the science concepts in a thing that's like that science concept. So our students are going to be talking about the limitations of analogies that they're showing you, but it's not to say that the analogy is bad, and we're going to be very kind about how we give critiques because the artist is in this room right now, and they're gonna have a chance to say what they intended to show with that drawing. So again, just a reminder to our students that we are going to be kind when we give critiques on the drawings that are going to be presented because all analogies will have limitations. All right, so this is our presentation order. We have 12 groups and we'll take a little intermission in between. And students will have 5 minutes to present on their picture, and then we will have 5 minutes of questions from the audience. So audience, I need you to participate, okay? You're not supposed to know any science, and you're supposed to be able to understand the picture. So ask any questions that you have. Any question is a valid question. And really, this Q&A part is really essential for your students. This is a very important skill to be able to think on their feet and come up with an answer, okay? So by asking a question, you are really helping your students, okay? And you will really help your students because if you ask an easy question, that takes up time so that Professor Tolbert and Dr. Rita Blake don't have time to ask the really hard questions. Okay, so again, we want our audience to participate and ask good questions. All right, so let's start with group 1. Come on up. Little bit of presentation housekeeping. Again, we've got our microphones. Green means good, means it's on. And then you really have to be uncomfortably close to the microphone for it to pick up your voice. So even audience members, when you ask a question, and I give you the microphone, make sure it's awkwardly close to your face. And then the way I like to demonstrate how to use the microphone is to be a pop star and not hold it like an ice cream cone. Okay? People have a tendency to want to hold it down here, but we want to be a pop star. And then when your head moves, the microphone moves with you, because if you turn and look at the screen and keep talking, nobody can hear you. All right? So just to remember, use the microphones well, because our YouTube live stream is going and they will only pick up what the microphone hears. And then remember, we have our laser pointer, which is this line button.
All right.
Okay. Hi, everyone. My name is Maddie Melville, and I will kind of be explaining everything first, but I think I'll let these guys introduce themselves first as well.
Hi, I'm Darren Kyle.
Hello, I'm Erwin Kanoglu.
Okay, so to start off, I'm going to be kind of introducing what we see here. So in order to understand the analogy, it's good to just look at what is in front of our faces. So here we have a scene of a person at a carnival and going through a series of games. So in our first panel up in the top left, we have a person shooting a basketball, and oh no, he missed the shot. And we can see that the people are saying, oh no, he was off by a very small number. And then in the panel next to that, in the top right, we have a person throwing a ball in a game that kind of, it measures how fast you throw the ball, and then you have to throw at a certain speed to win. And we can kind of see the math of that up at the top, just to see like if he won the game or not. And then at the bottom, we have two people at one of the games that measures your strength on how hard you hit a block and the thing goes up. And the two people in the bottom left are hitting each other with the hammer instead of the strength thing. And then on the other side, they hit the strength thing and it goes all the way to the top so that they win. And I'll be passing it off to Erwan.
Yeah. All right, thank you. So, pointer, okay. So this first panel, I hope you can see, but it's, we can see how he's 1 nanometer off from making it into the goal, or like winning the game, and we can tell that because of the dialogue. So this first panel shows how the nanoscale can affect the human world. So usually you can't see nanoscales with your eyes, but in certain cases you can see how it affects the real world, like when we do diffraction grading, and we saw the rainbow on chocolate, which is not chemically treated, it's normal chocolate, but the nanoscale makes it look like it's rainbowy. For our second panel, we see how he uses indirect measurement to see what he needs to win the game. So we see how he knows it's 3 meters, and he knows it's been 3 seconds since he hit the ball. So he calculates that he needs 1 meter per second to win the game. Most scientists use indirect measurement because sometimes you can't always calculate something. Like you can't calculate a planet, so you would calculate something else and then use that to calculate maybe like the volume of the planet, because you can't really calculate a volume of a planet. Now for panels 3 and 4, they're combined, so I'll just talk about them both. But for the first one, we see how nothing's going on. Like they're hitting each other, but they're not winning the game. So this type of interference is called a destructive interference, and it's when 2 waves collide with each other and they cancel out. Nothing happens. And for the second one, so panel 4, you see how they're both working together to hit it. So this is called constructive interference, where 2 waves hit each other and then they make a bigger wave. Yeah.
Was that it?
Yeah.
Okay. Minute 30? Minute 30? Okay, I got this. All right, so there's some limitations to this thing. So for some of the questions that they did not answer, there was something that we learned called a atomic force microscope. So essentially what this is and what is different from like a regular microscope is that it would use electrons instead of like light, as you can see up there in the ceiling, to see nanoparticles. And so because like it has to be really small, like electron size, to be able to see the nanoparticles, because if we use visible light, the waves are too large and we wouldn't be able to see them in the first place. And we can use like light. One other question that they didn't answer was like using light to measure both big and small objects. So for example, like I said, the AFM or atomic force microscope, we can use it to measure like light to measure small particles, and we can like, for example, like a Hubble telescope, we would use that to use light to like see far away into the galaxy and stuff like that. 30 seconds? All right. Okay. So the final limitation here is that, is like, you see him in the first panel, he's saying like, OMG, 1 nanometer off. So we weren't actually supposed to be using scientific terminology in this, and I'm not sure if a nanometer would affect a basketball range. Sorry to whoever wrote that, but but this could be easily remedied. Just like put it in like 1 centimeter or something like that, and that would totally like explain everything else and put the final like science concept that we learned in this experiment in. How many? Okay, that's it. I'm done.
All right, questions from our audience. Oh, see, parents, you gotta be real fast because Dr. Rita Blake is always ready with a tough question.
Okay, so my question relates to the bottom 2 panels. So you did mention that they represent constructive and destructive interference, which I agree, and you did start to describe them, but it sounded to me like you described them kind of the same way. So can you clarify because in both cases you're combining waves, so then what would the difference be then between constructive and destructive specifically?
Okay, I think I'll take this question. So the question was kind of about how destructive and constructive waves interact. So for destructive waves, it is when 2 waves are colliding with each other and they're both coming at each other kind of at the same point of the wave, and they kind of cancel each other out. Or like the constructive is when the amplitudes increase, so they create more energy or amplitude with that. So that was kind of described as how that they both hit it at the same time and they went all the way to the top. But in a destructive wave, they kind of cancel each other out.
Could you clarify that a little bit more? So with destructive interference, what is aligning? What parts of the wave are aligning? And in constructive interference, what parts of the waves are aligning?
Okay, I'll take this. So for constructive, they don't collide face on, but they do collide slightly offset, which like amplifies its amplitude.
I could take it. I took physics. I know what's going on. So anyway, so in the like parts of a wave, there's going to be something called a crest and a trough. So a crest is like the highest point of the wave, and the trough is like the lowest point. So essentially, during like constructive interference, it would be crest and like trough and trough. So like the ones that are alike are going to be lining up with each other. You got it? Okay. And then destructive interference is when like a crest and a trough align together, and then they essentially cancel each other out and create like a straight line.
Excellent. Other questions? We're not done yet. We got more questions.
Can you guys describe a little bit more about the experiment and like you kind of described like the indirect measurement, how that related to the experiment and the changes at the nanoscale affecting like how we see the chocolate, but where did you use the constructive and destructive waves in the experiment?
So in the experiment, let me just explain the experiment first. So we had a laser pointer, and then we had a diffraction grating that we did not know like the distance between, and we had to figure that out. So we shine the laser through this grating at a certain height. We change the height every, I think, 4 centimeters, and we would try to measure the distance between the gratings. So when we shine the light through, you would get a center point, and then you would see like points around those, not like circles, but like individual points that were getting weaker and weaker. So in the places where you can, in the places where you can see the light, this is where you get this constructive. But in the places where there's like nothing, like it's just there's no light, that's where destructive interference is happening.
Excellent. Maybe have time for one more question. Okay, I wanted to clarify a point about atomic force microscopy. You had mentioned that it's using electrons, and that is not correct. We have electron microscopy, which uses electrons. So could you please elaborate on atomic force microscopy and how that works?
Sorry.
We got some phone a friends happening in the audience here,
I'm sorry.
gesturing.
It finally clicked. I realized my mistake. So atomic force microscopy. Sorry, everyone in the audience. So essentially, there is going to be like this probe, and it's going to be 1 atom large. And essentially, what this is, it's like physically touching the surface. So imagine like a blind person reading Braille. That's the best. Why are you laughing? This is like a great example.
All
Okay.
right, so why is it atomic? So you mentioned it's a single atom tip, and then what kind of resolution are you able to get with the single atom tip?
You're able to essentially get like atom by atom. You're able to see like height. You're able to see like stiffness and like so on, like so forth. You get like a great map of like what the surface looks like on the atomic scale.
All right, great. Thank you, guys. All right, group 2, come on up.
Hi everyone, I'm Molly.
Hi everyone, I'm Jerry Liu.
Hello, my name is Joseph Levitt.
And today we're going to be talking about an experiment we conducted on Tuesday where we made dye-sensitized solar cells. So these are devices that convert light energy into chemical and electrical energy, and we measured their electrical output in the light and dark using a multimeter. These are an alternative to traditional solar panels, which are typically made from silicon. Oh, and now we're going to look at what the image is actually showing. So we can see with this analogy, there are parents taking their kids into a playground, sort of a circular shaped playground, and the kids are going on the slides, then they're resting, then there's a monitor monitoring the kids, and there's a difference between the small and the big slide.
Yeah, so once again, my name is Jerry. I will be going into the scientific concepts of this analogy. But before I do that, I want to shout out to my bro, Darren. Thank you for setting the bar so high. So yeah, here we go. So we see in the very top corner, the parents are introducing the kids to the playground, which in our group, we think it's the sunlight introducing the energy to the system. And we see onto the system, the slide represents the thing that the sunlight is hitting, in which on the slide, the kids represents the electrons. You see they climb up onto the slide and they slide down, representing the electrons getting excited into the higher energy level state, and then falling down back into the ground state. And then after the slides, we see the bench where the electrons or the kids are resting. We think that represents the iodine, which is responsible for recycling the electron in the system. And then after that, we see a monitor kind of like pushing the kids back into the slide, because who don't want more fun, right? So this kind of speeds up the process, like by pushing the kids forward. So we think that's the catalyst we used in this system, which is the graphite. And we can see also the cyclic nature of this system, because the kids are like endlessly going back to the slide, and then I don't know if this counts as child labor or not, but yeah. Also, we can also see there's like a difference in the size of the slide. We can see there's a smaller slide in the middle, and we think that is supposed to be a representation of the voltage and the current, because we can see on the bigger slide, because the energy level or the height of the slide is higher, so there's more kids going through. We can see there is a max 3 kids per slide. I don't know if it will fit, but yeah. And then on the smaller slide, we see, because it's shorter, the sign says only 1 kid per slide, which I think is safer, but I'll hand it on to my partner here.
Yeah, this is a great analogy. However, there is some limitations, such as with the voltage and current with the slides, not always the voltage will always correlate with the current. And then another thing would be the slide represented as the dye and TiO2. The dye is a different process than the TiO2 would represent in the system. The dye, as the sunlight excites the electrons, as the kids climb up the ladder, the dye would pass on the electron to the TiO2 to let it hold on to complete a circuit. In the circuit, there is no way where we can see where the electron is getting de-excited outside the slide. And so there would be, so there's no electrical output. Now with the iodine and graphite, the graphite is a little bit ahead of the iodine, not allowing the graphite to directly correlate a catalyst, helping the iodine to do a redox reaction. And so allowing a redox reaction will allow the electrons to get back on path to get back to this slide. And now it also does not mention the economic benefits of going solar in today's economy by many governments are providing subsidies for solar panels for their people. Thank you.
Okay, questions from our audience. Students, you're welcome to ask questions as well.
So my question is about the current and voltage element of this. I do think that there is something that is distinguishing what elements of the slide is related to the current and what elements of the slide is related to the voltage. So can you describe a little bit more what is the difference between current and voltage? And then based on that, maybe what part of the slide analogy is the current and what part of the slide analogy is the voltage specifically?
So we did discuss a little bit about that. So what we think is the voltage is the height of the slide, because the voltage is determined by how high the electrons can jump and the energy levels, and that determines the voltage. And the current is how much electrons that are actually going through the circuit.
So how is that part represented in this?
Oh, so in this case, it's the kids sliding down the slide.
Yeah, so the number of kids that you can have on the slide. All right, other questions?
Darren, I think you have a question, right? Don't try to be nice. You were mean to me.
I'll sit here and stare at you all awkwardly. Your kids had to deal with this too. When I asked them for volunteers and no one would volunteer, I would just sit here and stare at them.
So one thing that you mentioned that this analogy did not have in it was the economics of solar. So in thinking about what you did learn about the economics of solar and the ways that it's been made cheaper, can you maybe just on the fly think of a way that you could include that in this analogy? Is that possible?
Okay, so one way that we kind of discussed is that instead of just making this like park or something like free, we can go a little bit into capitalism and like have tickets, and then by showing how it's more economically friendly, we can say, oh, it used to be like $100 per kid or something, and now it's 20, so that and we can also label it as all subsidized by the government. So that really shows the subsidies that the government gives in this industry.
All right, great. Do you have one more? Yeah, just for the benefit of all of us here. So what parts of solar have gotten cheaper over time?
So I'll answer this question. Parts of the solar that's been getting cheaper over time is the actual manufacturing of solar. By having more larger factories, it's cheaper to produce more than having a smaller factory and producing less product in general. And then also the engineering has been getting better over the years, allowing for cheaper processes to create these solar panels in general.
All right, great job. I forgot to acknowledge the artist of the first one, but let's acknowledge this artist and then we'll go back to the first one. So who's our artist? All right. Introduce yourself, and then if there are any additional comments you have about your drawing.
Hi, my name is Cameron. I drew this, my intention with drawing like the slide was like the dye and the TiO2. So like the dye was meant to collect like the excited electrons, which is why it says like I can't wait at the top. And the TiO2 was also meant to like carry them further, which is why they say like we as they're going down the slide. But other than that, you guys got like everything else that I was trying to show in the analogy. It is not child labor, by the way.
Can we ask questions?
You have a question for the artist?
Yeah.
Okay, real quick.
So in this system, we don't really see how the energy is used by the electrons. We just see them sliding down into the ground state, which usually indicates that the energy is used. Is there something that we're not getting, that somehow the energy is being used?
It's an analogy for a reason, so like I couldn't include everything. So there are, there are gonna be limitations. So like no, there's no way of showing where the energy is going.
Okay, thank you, group 2. Okay, and then I just want to go back real quick and acknowledge our group 1 artist. So
I'm Milo, but yeah, I think they covered it pretty well. I was just trying to make some cute drawings, so I think I succeeded in that, hopefully. Yeah.
All right, thank you. Did you want to say something? Okay. All right, and so Professor Tolbert is here with us now, so she's going to say a brief thing. And group 3, get ready.
Yeah, group 3, come on up. Okay, so hi, I just want to introduce myself. My name is Sarah Tolbert, and I'm a professor in the Department of Chemistry and Biochemistry and in the Department of Material Science and Engineering, and I am the instructor for this class. And it has been a pleasure to have your students here, and I have tormented them only a few occasions during this week, but now I get to ask them more questions. My comment to parents, I have had kids here, my own kids have taken this class, and asking questions is one of the most important parts of learning to give a presentation. Anybody can give a presentation. You can just practice it until you're happy. The fear in everyone's heart is somebody will ask me a question and I cannot answer the question. And what you learn eventually is you may not have a perfect answer to the question, but you can answer a whole lot of questions. And the only way to realize that is to, in fact, answer questions. And so your job as parents is to ask the presenters questions. And to motivate you, I will just say that if you don't ask them questions, I will ask them questions. And I bet your questions will be easier than my questions. So please give the students an opportunity to answer a wide range of questions. It's super important for learning to be a science presenter. And so do your part in these final presentations.
Hi, my name is Tarek Shaker, coming senior at Santa Monica High School.
Hi, my name is George Skinner. I'm an incoming junior at Palisades High School.
Hi, my name is Cherie Lee. I'm an incoming junior at West Point Gray Academy.
The analogy we are going to be discussing corresponds to the biosensors experiment that we did earlier this week. In this analogy, we see chameleons changing colors and their hearts responding with higher intensity to darker colors in response to them getting matched with each other and being in a warmer area, helping them mate faster. You also see a toucan on the bottom right panel eyeing a chameleon in the tree.
So as Tarek said, this experiment was on biosensors, specifically colorimetric sensors. In biosensors, there's a signal, which is an external factor that the sensor is measuring, a transduction where that factor is actually measured and we get a response, and the response which shows us what the results mean. A colorimetric sensor is a form of biosensor, so it uses those 3 steps, but the most important part is that the response is a color, and we compare that color to different colors that we got from known values in other experiments. And some of the other parts are an enzyme, which helps speed up the transduction and give us our response faster. And we can also encapsulate the biosensor in a nanoporous bead, which works like a bubble to protect the reaction from other outside factors. So in this analogy, we see the signal in that top section, which is the 2 chameleons seeing each other, and the transduction is this chameleon's heartbeat speeding up after it sees this chameleon. And the response is the chameleon changing color and kind of blushing. And then the calibration curve is in this section over here, which shows the chameleon comparing itself to the different colors of the other chameleons to see which one it matches up with. And the enzyme is in these 2 panels. We can see that it requires less energy, which is how an enzyme works. It lowers the activation energy for the reaction. So these 2 chameleons are in an area with a higher temperature, which helps them mate faster. And then in this last panel, we see that the chameleons are inside of a tree, and this toucan is kind of angry, so we think that the toucan wanted to eat the chameleons, but it couldn't because they were protected by the tree, which represents the bead.
Yeah, so we think that this student did a wonderful job of capturing the main 4 questions. However, we did notice a couple limitations with this. So we can see from the drawing that there's a comparison of color through the different shaded chameleons on the branch. However, we don't see a very clearly established preference of the chameleons. We understand that they match with those that they share a shade of pink with. However, it doesn't necessarily show the incompatibility of the mismatched chameleons, which could possibly support the calibration curve. Another limitation is the clarity of the enzyme's involvement, which George mentioned that it was the temperature of the environment showed in the 5th frame. Yeah, it was the temperature of the environment speeding up the mating process. Providing a spike in temperature and demonstrating the contrast between a neutral and hotter zone and its effect on the mating process would have helped differentiate whether the thermometer represents the temperature of the chameleon's body or the environment. So, yeah.
Thank you.
Thank you so much.
Okay, questions from our audience. By the time my tiny steps reach Professor Tolbert, someone else is going to want to ask a question. No takers? No takers?
So for the colorimetric sensor, you mentioned that the similarly colored chameleons tend to match together, and you mentioned something to do with an unknown. Can you explain in the experiment that you performed that day how it was
you determined, like what value did you determine from your unknown using the standard curve?
Basically, how do you use a calibration curve?
Oh, I can take this one. So when you're, after you put your input into the sensor, it will leave you with an output, which is just a color. When you have a calibration curve that comes from previous experiments that you know, usually the concentration of something. So if something is like a more intense color versus a lighter color, then you'll be able to see, like you have noted down which each one corresponds to. So you compare your result to whichever one it's closest to, and you know that it's probably closer to that value.
So in your experiment, what were you guys trying to measure?
In the experiment we did?
Yeah, in the actual experiment.
We were measuring the sugar concentration of different unknown liquids.
Sorry, I'm still trying to get my bearings because I just walked in. This analogy does a really nice job of getting across the idea of a calibration curve and matching that. The one challenge is, how do you represent what you're calibrating in terms of, you know, in your experiment, you were doing a concentration of something. And this is sort of a state of mind of small creatures. So can you think of any way that you could take this analogy and bring in some sort of more quantifiable external state and add that? And then I just want to add that in discussing this for all the groups, so every analogy is limited, and that is, we talked a lot about how that's sort of intrinsic to making these analogies. So this is just a language comment, which is, instead of saying, well, one thing this analogy didn't cover or one thing this analogy left out, definitely use words like, a limit to this analogy is that it doesn't capture this aspect of the physics. And then use that as an excuse to explain the actual physics, as opposed to as an excuse to critique the picture, because it's not a critique. You can't capture everything. So it's fine to say this is a limit to this analogy, but then just say, so I will now explain to you the piece of science that was left out. Or if you have an idea, you can say, if you added this, that would be a way to include it into your analogy. So you could come up with a cool idea, or you can just explain it. But don't use it as a critique, use it as a science discussion. Okay, but so now I'm giving you that opportunity. Is there any way that you could think of to map this more onto something external, like a concentration, as opposed to a state of mind?
So I can kind of take this one. So we mentioned within our limitations that there wasn't a clear, comparison of how it would turn out if two chameleons that weren't matching in color, how they would be incompatible, and why it's better for them to match up with a certain shade. So or at least I think that a way that this analogy could be better supported would be if they showed maybe a reference kind of chart of chameleons with the same matching shade. They might produce more offspring or something, compared to if they were to match with another one, maybe they wouldn't produce as many offspring. So I feel like that could support the fact that the calibration is that that's a specific preference, and that is the better option out of the rest of the colorimetric options for them to be picking the one that they're matching with.
Yeah, that actually, I like that idea, because you could get across a lot of concepts that way, but I think that's not quite the answer to the question. And I don't have an answer, by the way. It's not like I have a brilliant idea of how to do this. I'm just throwing it out there, because that's always the interesting thing, is can you imagine a way to extend the analogy even more? But the idea is that concentration is sort of a quantifiable external property of a creature or a solution, and amorousness is a state of mind. And so I'm not sure if there's a way to make a more external property that could be mapped on to amorousness that could be more analogous to sugar concentration. Sugar concentration is a number.
Maybe like in terms of like the transduction aspect, like the faster heartbeat, maybe it could demonstrate like something like that.
Heartbeat would be exactly the kind of thing.
Yeah,
that
something
I'm
like
talking about.
quantitative.
Something that you could quantitatively associate with them. Yeah, if there was a way to draw heartbeat, that would be a great example.
Or showing like beats per minute or something like that. Yeah,
that would be a great idea. Okay, thank you.
Yeah, I think, and I don't know how chameleons work, but like you could have said something like if their body temperature correlates with the color that they show, right? So that was kind of I don't know if that's how chameleons work though. So, okay, thank you guys. And then our artist for this one.
Yeah, that was pretty good. I mean, the idea behind it was just like chameleons change color, so that was sort of the idea of the day. And then I looked up like, why do they do that? And it was if they're fine, they find their mate. So that was like the whole idea. And then the bottom also is not a toucan, it's like their main predator. So that's it did need a little bit of like research behind it, which is another limitation also.
All right, thank you, Molly. Okay, group 4.
I'm Milo.
I'm Lawrence.
I'm Julie.
All right, so context here is that this represented the experiment we did yesterday with photolithography. So what you literally see is a person pouring adhesive onto a parking spot and then putting over the handicap stencil over it and then painting over it with a paint roller. And then after that, they wipe off the excess adhesive and then they take off the stencil and darken the borders. And then the last step is to remove any leftover adhesive. Below that, there's 2 instances, one where a fan is used and one where the fan wasn't used. And when the fan was used, you can see that the image is more clear compared to when the fan wasn't used. And then to the right of that, you see that there are stencils on the road that say go and stop, and what we thought is that that sort of regulates the traffic. Below that, you see where it says instead of a parking spot, they use a scaled down version of the handicap symbol on a sign, and they did that with a paintbrush. And then on the bottom, you see one person doing the whole process by themselves. And then to the right of that, you see a group of 4 doing that, but each with different roles. And then finally, there's a 45-minute parking label where there would be a handicap symbol, but they moved the handicap symbol to a sign, which, yeah.
Okay, so in these top 6 panels, like all up there, it's displaying the steps of photolithography. So first the adhesive is put on, which represents the photoresist, and that's just to help stick the stencil on. And then next you see the stencil, which represents the mask, and that's just to like set what's gonna be made. And then next the paint roller is put on to represent the UV exposure, and essentially it kind of marks in the stencil and makes it like what's actually supposed to be imprinted on. And then right here is just kind of setting in and developing in photolithography. And then once they take the stencil off, it represents like the etching. They're etching off all the excess material. And then lastly, stripping. It's like stripping off the leftover adhesive that was left over. So, and then down by the fan, so the fan can be seen blowing away dust. And this is in order to keep the handicap stencil clean, because on the right, there's dust on it, which cloudies up the image. And this is kind of like representative of the clean rooms that are necessary for photolithography, because photolithography is done at a nanoscale, and dust particles and other particles like that can kind of interfere with it and damage the stencils. So that's why we need clean rooms. And then also on the very right with stencils on roads, it just shows go and stop, which is kind of representative like an on and off switch in a transitor. And those are used in computers at a nanoscale level. And it's kind of just correlating go and stop with off and on. And then with the parking spot, and you see the handicap label being on a sign rather than the ground, you could see it's done with like a smaller tool, like a smaller brush, as in like smaller wavelength to do smaller feature sizes in photolithography. And then also how feature size can affect like function, like it's more functional now, because on the very bottom right, you see you have a sign, but then you also have more information, 45-minute parking, so that can like convey to whoever's seeing that like more information, right? And then on the bottom, it just, these people, the singular person and then the 4 people working together in unison is more representative of parallel and sequential processes, and like, which is just a sequential process is like one action being done at a time, and then parallel is like multiple at the same time for more efficiency.
Okay, so for a limitation, for the first part, it is a process. On the step 4, it doesn't really show like the patterns developing, like how the pattern stays on it. And also for step 5, for photolithography, the mask actually should be removed right after the exposure, but on the picture, it was removed when etching. And also for the dust, actually in reality, the dust doesn't really matter because we're gonna park on it, so it's getting dirty anyways. And also the dust kind of affect things because it's on a macro scale, and we are protecting materials from a nano scale, so that's why it really matters. And also for the stencils on roads, in reality, we actually control the flow by signal lights, not really on the signs. And yeah, and also for parallel and sequential ones, it's kind of confusing and not really show the difference on the efficiency. Probably can add like the time difference.
Okay, I just want to start out by reiterating what I was saying before about limits of analogy. So there's definitely limits, and I have some questions about those. But I really want you guys to use different language in discussing them, because you're not critiquing the drawing. Nobody's job is to critique the drawing. Your job is to say, as an analogy, where does this correspond to the science and where does it not? So that's different language. And everybody is an amazing author, and I think it's important to realize that we're not critiquing the drawing, we're talking about where the limits of the analogy is. So with that, let me go back and ask, in terms of the photolithography process, there is the big idea is pattern transfer, and this pattern transfer is well described here. But there are many aspects of the pattern transfer in photolithography that are different than the pattern transfer that is done here. And so what I would like you guys to answer, and you've probably said it in different ways, so I just want you to say it in a more compact way, is how is the pattern transferred in photolithography, and how is that different than the pattern transfer in this drawing?
So in photolithography, there's like 2 layers, right? And then the UV kind of just goes through it and then like marks through the stencil, and then it's like 2 layers of marked in. And then just like the etching, it just takes off the first layer, and then like everything's like on there. But then here it's kind of just like there's only 1 layer. It's sprayed on rather than like actually like dug into the ground, which isn't just isn't how stenciling works. So that's like one of the limits of
Do you want to add something?
Yeah, I want to say that like in photolithography, it's more on the nanoscale, whereas this is like on a bigger scale.
Yeah, of course. So yes, definitely. This is a macro scale version of the nanoscale patterning. So for sure. So if I were to describe this, I would say in photolithography, you first have some mask and then you UV expose it and then you develop it and you then have a mask pattern. That's where this starts. It starts with the mask pattern that you're just putting on. And then the second thing is that they're reversed. In this case, you're adding inside the mask. And in photolithography, you're taking away around the mask. So this is what I want you to do, is to analyze, to say where does this analogy sort of join the flow of the actual photolithography experiment? Because really what this is trying to get across is just the idea of pattern transfer. Okay, but so those were all good answers.
Okay, so for the dust part, so you said that it doesn't really make sense in the macro world, and I agree. But could you think of something else which the fan may be able to blow away, which would be important on the macro world, like for the actual painting itself?
You can see the fan blowing it away. Maybe it would actually matter, like, say the dust gets like so heavy it can completely obscure the painting. So then at that point it would really matter in the macro world. So in that it does matter, but yeah, we said a limitation was that like you can still see the sign, so it's gonna still show up, just not to the greatest extent, but it's still apparent, right?
Yeah.
Okay, thank you. And then our artist.
My name is Alexandros Likos, and I think everything they said was pretty good. And I believe the limitations they said were truthful. I would agree with them.
Thank you. Okay, group 5. Okay, so while they're coming up, I just want to preface that we did have an experiment this morning. So your students performed an experiment this morning, and 2 groups, so 6 students total, volunteered. It was a little bit of teeth pulling to get them to volunteer, but they volunteered to really focus during this morning's experiment and then draw one of these drawings during lunch. Okay, so they just drew this like a couple hours ago. And so this group drew one you'll see later, and then the other group drew this one. So, and they just learned these concepts this morning. So thank you again for volunteering, and thank you for presenting on this.
All right, so hi, my name is Cameron. I'm a rising junior, and I go to Santa Monica High School in Santa Monica.
Hi, my name is Lalit Das. I'm a rising senior at Lee High School from San Jose.
My name is Aiden. I'm a rising senior in John Marshall High School that's located in Los Angeles. And our group is here to walk you guys through this analogy.
So I'll start off with what we literally see in the drawing. So as you can see at the top left, we see a water bucket and a hose kind of coming out of it and spraying the water all over the flowers. Next, we see someone saying like, oh no, it's out of water already. And they're kind of upset like because it only happened like 2 minutes later. The next day, they actually put in place a drip irrigation system, which is now spreading water to the flowers with a real water bucket instead of a toy one. But unfortunately, 6 hours later, too little water was coming out and the flowers unfortunately died. The day after that, they have a whole new system again with a somewhat bigger hose and a new water bucket that is watering the flowers, and it actually works because there's a balance of water and output time. So we think that this analogy relates to, of course, the lab that we did earlier today surrounding supercapacitors, where we created carbon dough, which was used to store charge on its surface inside the supercapacitor, and citric acid that acted as electrolytes in order to power a circuit ultimately to light up an LED light.
So yeah, this analogy is a really great job of describing this. Primarily, it highlights three things that we are trying to balance when deciding between capacitors, supercapacitors, and batteries. Those being, your energy input, your energy output, and the the storage capabilities of your system. So the first drawing here shows a small water bucket, which first is really easy to fill because it's small. Also, we have this hose here, which gives out a lot of water really quickly. But as shown in the next panel, it runs out really fast, which is representative of a capacitor, which again is able to charge really quickly, dispense its energy quickly, but then doesn't have very much storage. But then in the next image, we see this drip irrigation system, which has, as the author states, a real water bucket, meaning that it has significantly higher capacity. However, because it's a really big bucket, it takes a lot longer to fill up, and we have this drip irrigation, which gives out water droplets, individual droplets, instead of a big stream, which means it's a lot slower. However, the problem with this, again, is that because our flowers need water, it's too slow and then they die, which represents some of the problems of a battery, because sometimes it might not be fast enough to give enough power. And finally, we have our compromise, which is a slightly smaller bucket with still a little bit less flow, but it also charges a bit faster than the battery. And what this means is that it can, support the flower without running out too quickly. And this is like a supercapacitor.
Before going into the limitations of this analogy, I would just like to once again highlight the fact that the group of people who made this did this under roughly an hour with an experiment we did today. While most of the other analogies were done for homework, this one was done in a limited time, which is very impressive. So little round of applause for that. Anyways, what we see here, very handsome man, beautiful flowers, probably growing these flowers for a significant other, don't know, making this up. But yeah, unfortunately, this analogy is an analogy and it does have some limitations. First, I would like to go over the realistic concepts of, actually, before the realistic concepts, I'd like to go over one thing that our group noticed, which was the fact that the very first mechanism and the very last mechanism are very similar in design, so it might be a little confusing for audience. And as well as the end result of both the first mechanism and the last mechanism, they both have flowers that look relatively healthy and, like I said before, beautiful. One thing they could have done to change this, maybe change up the design a little, and as well as add the flowers are maybe they don't have enough water, and they're wilted a little. And realistically, 6 hours and 30 minutes. I don't know if you guys have ever grown plants, but this is kind of unrealistic amount of time to water these living organisms. So another thing that could be changed would be the time to match what would actually be occurring. I get that this was done so that it could match our experiment we did today, which was about batteries and supercapacitors. But yeah, this isn't very realistic. And finally, I would like to address the fact that this doesn't really address the concept of surface area, which was a very important thing, important concept in our experiment with regarding the capacitors. But overall, this analogy done under roughly an hour, very good, and it gets the point across. So thank you.
Okay, so I'm still on the sort of how we think about these kinds of presentations. The fact that they picked actual realistic battery times as opposed to realistic plant growth times is a perfectly fine choice. One of them is going to be wrong, and so picking one or the other, I would say, is not a limitation. It's just a choice. But the concept of surface area and basically structurally how a supercapacitor stores charge on the surface of a flat surface. Capacitor stores charge on the surface of a flat surface a supercapacitor stores charge on a nanostructured surface, and a battery stores charge in the bulk, is something that is not captured in this. And so my question for you is, how could you change your spigots or your spouts or your watering buckets to start to capture that concept in this analogy?
So I can maybe think of something for the difference between a capacitor and supercapacitor. So a capacitor could just be like, maybe we have like a plate and we just have some water directly on it, so it's not very thick layer of water. Whereas maybe supercapacitor could be like a sponge where you have lots, which like takes a bunch of water. It's on like the surface of all the pieces of sponge. There's a lot more surface area, so it can store a lot more water. I'm not sure what you could do for a battery though.
So I mean, one thought, if you had a whole pile of flowers, for the capacitor, you could have a single stream of water in the middle, which doesn't necessarily water them all, and you could try to get the idea of the increased surface area with the supercapacitor with a big stream of, more like the picture, many streams of water. The bulk would have to be probably not a watering can in some way to capture that.
I just had a quick idea for the battery. Since you said bulk, I was thinking maybe it could have been represented with like multiple like buckets of water for the irrigation system that they have up there. That's just a thought though.
Yeah, maybe you could actually not have a bucket for the capacitor and the supercapacitor and have a bulk bucket for the battery and keep that drawing exactly the way it is. The point is, I'm trying to just get you guys thinking about how any analogy, there's like crazy ways you can make it a better analogy to the science if you have the science in your head. But those are all good ideas. Good job.
All right, who is our art? Oh, our artist is the other group. So other group, did you have any comments?
Yeah, so I definitely agree with what you said. Like you mentioned, it was a time constraint. I think we ended up having like 10 minutes of planning and 10 minutes of drawing. So we first decided to focus on the balance between water and output time. But definitely, as all of you mentioned, the surface area would have been the next thing to cover. So I think it was really good to point out to the audience that that is something important, because that was like a huge focus of our program. That a great benefit of nanotechnology is that the surface area of the object is extremely increased. And shout out to the other members of my group who like designed this along with us.
Yeah, good job.
We chose like the drip system and then the buckets, because the idea was the drip system is like attached to like the pipe, so it doesn't really run out of water. It just has, I guess, an unlimited supply of water. But if you have like a watering can or a bucket, you have to. Actually, we did draw that up there, but yeah. Okay.
All right, thank you. Group 6.
Hi, I'm Alicia. I go to St. Francis in Sacramento.
Hello, my name's Antonio, and I go to Gunn High School.
Hi, my name is Catherine Lowe. I'm from China.
Okay, I'm going to be introducing what we see. So this art just focuses on an artist with a bucket and a string. He uses the art and swings it around over the canvas on the floor. In panel 3, we see the paint spilling at an angle. In panel 4, we see 2 buckets colliding in panel 5. And then in panel 6, we see 2 buckets going together. And then in panel 7, they have art.
Okay, so now I'm gonna explain the science concepts in this picture. So first, in panel 3, we have indirect measurements, which is it's the way to measure something that's pretty hard to measure by using 2 things that are easy to measure, or just multiple things that are easy to measure. For example, in panel 3, we can see that the paint drops like at a certain angle, a certain distance. And with the triangle, we can by knowing the distance that the two legs of the triangle are, we can use the Pythagorean theorem and some other formulas to find the distance and the angle that the paint drops at.
And we
Wait,
think.
wait, wait. In panel 5 and 6, or 4, 5, and 6, this shows constructive and destructive interference, which is the constructive and destructive interference is when, like for constructive interference, when two light waves collide into each other, and they have like, if they're both at the peak of the light wave, then they combine into like a bigger light wave. And for destructive interference, if like one light wave is at the peak and one light wave is at the trough, then they will cancel each other out. So in number 4, this shows destructive interference because they're opposite of each other, and when they collide, it completely cancels out the movement of the paint, and there's no painting done. And for number 6, it's constructive interference when the two paint buckets move in the same direction, and then they both spill to create a pattern on the canvas.
And we think this is a great analogy as it expresses the concepts of constructive and destructive interference well, and also indirectly measurement. But there are also some limitations. The first is that the measurement in panel 3 is kind of vague for us. And also some of the audience may not know what's being measured. So to improve this, we suggest that the drawer may add some rulers or protractors to show that it's measure the angles or the distance. And also this analogy doesn't include other key concepts such as how the light can be used to make measurements both big and small, and also the atomic force microscope, and how does it resolve smaller objects than other light microscopes, and also how changes on the nanoscale affect changes on human scale.
And that's about it for our presentation.
You guys mentioned some concepts that they didn't cover in this analogy. Is there a way you can think of to incorporate them, or do you want to explain the concepts that you mentioned a little bit more, and how they might relate to this?
Yeah, I just want to add that the things that they didn't cover, it's not an opportunity to critique. It's an opportunity for you to explain. So anything you say wasn't covered, you have to explain what it is, what the actual science is, even if you can't think of a way to incorporate it, because it may be impossible to incorporate.
Yeah, I honestly don't know how to incorporate those questions into here, but I can explain some of them if so some ways to use light to make either big or small size measurements. So for a galaxy size measurement, you can send a beam of light to the moon or whatever, and then measure the amount of time it takes for it to come back, and that'll be you can measure the distance that the moon is, probably. I'm not even sure. For the atomic force microscope, so it's a microscope, someone explained earlier, I think Darren. It has a small tip, atomic size tip at the tip, and it repeatedly touches some object to measure its topography, or how stiff the thing is. And for the third question, how does nanoscale changes impact the human scale? It's just if there's enough microscopic changes, then it'll eventually make a big impact, probably.
So just following up on what you were saying, so I think this is actually the second time today we've heard you guys say, when thinking about light and measuring things big and small, you mentioned AFM. But just to repeat what was said earlier, AFM is not light, and you actually described AFM really well. But can you describe then a bit more how then, like which instrument is using light to measure small things, and what is the limit of size you can measure with light? Like what rule did you guys learn? Like what equation did you guys learn when you went to the light microscope labs that told you the limit of what light can measure?
Okay, so the microscopes that use light to like measure the size of something, or like measure just anything, they like project light waves onto the object, and it like takes like when the light reflects back, it generates a picture using the lights that's reflected back, and the size limit that she mentioned, wavelengths of light are like visible light usually has like around 400 to 700 nanometers in size. And for example, if something is smaller, like if there's like a crevice that's smaller than like, for example, 200 nanometers, then the light isn't able to enter and it'll just get reflected out, and it'll just be like a smooth surface when there's actually like a little bump in there.
So why did you pick 200 nanometers?
That was just smaller than 400 nanometers.
Yeah, it was a great number. We thought you picked it. It was the right number. Do you know that? What's the name for the limit? How small you can see? Anybody remember?
It's also a word you learned during your experiment. Like one of the key words you learned in this experiment.
And anybody in the class can chime in. Anybody remember? Yep, over there. Somebody had a hand up. The diffraction limit. Anybody remember what the diffraction limit is in terms of the wavelength? Lambda? Since you got the answer right, you know what it is. It's lambda over
2.
2, yeah. That's how small you can see things with light. That's why you need to feel littler things.
All right, who is our artist?
Hi, my name is Cherie Lee. You guys got it all perfect. Yay. That's pretty much it. It's a very simple analogy.
Thank you. Okay. We are going to do a brief intermission. What do you think? 5 minutes? All right, we're going to do a 5-minute bathroom break and whatnot. So everyone will be back here at 3:32. Okay, group 7, if you're ready, come on up. Even if you're not ready, come on up.
Hi, my name's Amelia. I'm an incoming junior at Campbell Hall.
I'm Kingston. I'm going into 12th. I'm from San Diego.
I'm Calvin. I'm going to my junior year, and I'm from Davenport.
So first we're going to explain what we can literally see. So we see the raw ingredients going into the factory, the drink store. The drink is being made, brought to the customer, and then when the customer is done, it's brought to the recycle center, and then the bottle is reused to make more drinks. And yeah.
So yeah, she just explained what's going on in the drawing. So I'm going to explain how this drawing is an analogy to the solar cell process. So starting up at the top right, you see a truck, and it says shipment for all type of raw ingredients. So that's an analogy to how the sun gives energy to the solar cell. And then so the energy enters, so the ingredients enter the drink store in which they're made into a drink. And the drink itself are the electrons. And then the bottle is the dye because it stores the energy. And then the packaging is the titanium that holds the dye. And then after the drink is made, it's exported to a customer, which is like basically the dye being, like the electron being sent out. And then the customer is gonna consume the energy or the electron, and then the used bottle is left, which is the left out dye. And then the dye is gonna enter, or the used bottle is gonna enter the recycling center. And you can see 3 people, like hopefully they're not like children, but there's 3 workers, and they, it says 3 workers that wash 2 bottles and get rid of the packaging. So that's the iodine step in which the dye is replenished. And then the boss on the left, the guy with the top hat and the mustache, is an analogy to the catalyst or the graphite, which speeds up the iodine reaction. And then after all that, the clean bottles are sent back up, which is basically the dye being replenished and ready to use again. So yeah.
So I'm Calvin, and I'll be going over potential changes and limitations. So first of all, I'd like to point out that I'm not great at drawing, so I don't know why I'm doing this part. But so the first thing we notice is that there's 2 bottles mentioned at the bottom during the recycle center. Now, I'm not sure if I missed something, but during our DSSC part, we did point out how the quote tired electron undergoes a iodine redox reaction in order to be somewhat replenished. And I believe that's what the 3 workers stand for. However, we still couldn't figure out what the 2 bottles at the bottom meant. And even after going through all the other requirements for the solar cell lesson, we weren't able to match it with anything else. And I'd also like to point out that for the TiO2, it's used as a holder for the somewhat excited electron, so the energy of the charged electron isn't lost as heat. But in the drink store, there's not really a sense of urgency, and I believe this could be changed by, instead of adding a packaging, to sort of add a preservative in order to make it more of a holder. And lastly, I'd like to point out that at the end, sort of towards the end before the reuse, the clean bottles is shown as the replenished electron in a way. But however, when the bottle is packaged with the drink, the whole drink is sent out along with the TiO2, which is, I believe, the packaging, and the drink, which is the charged electron. So I believe that that part could be a little somewhat changed. so that only the electron is sent out. Thank you.
Thank you.
Okay, so I was just wondering if, I'm not sure if you guys talked about this, but where do you think that this artist included electrodes? And if so, where
Yeah.
would it be and what is it?
The electrode is just the pathway that the bottle is taking. Like in a solar cell, the electrode is the path that the electron is taking.
I actually thought about this as well. I think the electrode isn't really there because it's supposed to be a path, but it is just arrows showing where it goes and not the like physical path, I guess.
Okay.
So just for clarity, you guys are indicating that the electrode is the part where it says export, it goes to a customer, it's used, and then it enters again. You think that's
Yep.
yes? Yeah. Other questions?
You guys talked about the recycle center, like not knowing what the bottles are for, right? I'm pretty sure the bottles were the electrons, and like the whatever chemical it would like renew the electrons for the reaction. I'm pretty sure that's what the artist was trying to do.
So actually, the bottles are the dye, and yeah. So, sorry, but the electrons were already used because the customer drank them. I'm not wrong.
Okay, so guys, the key, one thing. So there are some parents here, and you are having no mercy on them. And I can tell you that as a parent, you guys never have any mercy on parents. But the first thing that you need to do is actually really simply describe the real system so that then you can compare it. And you're just jumping in, this is the electron, this is the dye, but you're not saying so to give a clear science presentation, the thing to do is first say, in the real system, this is what happened. We had a light absorbing dye that, that had absorbed light and electrons were excited, then they were transferred. Go through each of the steps. And then you can make the analogy more cleanly. But if you look at this and say, what moves through this cycle in this picture?
Well, the
electron.
electron.
Forget the analogy. In the simplest thing, in this picture, what is the thing that is in every panel and is moving all around?
The water bottle.
The water bottle. In a solar cell, what is the thing that moves through the cycle?
The electron. It isn't. The electron doesn't disappear once it's used. It's just simply like weaker. So I think.
Yes. So yes, what you said is correct. Electrons do not disappear. If electrons disappeared, you would have E equals mc squared versus energy for the mass of the electron, which is a nuclear explosion. So the electron does not disappear. It is merely a high energy electron or a low energy electron. So it's moving around. You cannot get rid of an electron. So based on that, what do we think the water bottle is?
I think the water bottle is the electron, and that the dye could be the drink put in the water bottle.
Can I say something? So, I believe that the drink itself is actually the electron because the customer is supposed to represent like where the energy from the electron is going to, like it's powering that. It could be, the customer could be a light bulb that is being powered by the electron. So yeah, and the bottles are the dye because the iodine reaction in the bottom is replenishing them and cleaning them for reuse.
So what Professor Tolbert was saying is that you don't lose the electron, right? And if you're saying that the drink, the beverage, the liquid inside the bottle is the electron, then when you go to used bottle, your electron is gone. right? So what would the liquid inside the bottle represent? If before it leaves the facility, it's full, and then when it enters the recycling center, it's empty, what does the liquid represent in terms of an electron?
The energy?
Correct. So the liquid is the high energy state when it's full, and the low ground state when it's empty.
Yeah, that I was basically saying that. Sorry.
But that I just want to point out that still goes with what you're saying, in that the drink powers the person, the energy powers the person. And so what you noticed about the drawing was correct, that the contents of the drink is what is powering the system. When you make an analogy, diffuse non-real things like energy can be stuff. And so that's what we got to remember, that everyday analogies to science concepts are confusing, and many things can represent different stuff.
Right.
Yeah.
All right, so let's go to our artist.
So my name is Jerry, and I presented earlier. Special thank you to Professor Tolbert for keeping my analogy understandable. So the water bottle is in fact the electron, and the truck that is bringing in the shipment is the sunlight. They bring in the materials to make the drink, which is energy. So after you make the drink, which is pretty much where the sunlight hits the electron, the drink is in the bottle, which means the electron is energized. So that's why, yeah, probably it's my bad drawing that creates a little confusion. And another thing that I want to point out is that the numbers in the recycle center, 3 workers and 2 bottles, is that the reaction is actually 3 iodine molecules that recycles 2 electron. That's why the numbers are there. Yeah.
All right, thank you. Okay, group 8.
Start, just introduce your name, and then we'll go around, and then you go on.
Hey, well, I'm Hardy.
Hi, I'm Tanisha.
Hi, I'm Michelle.
And this analogy, it literally shows the experiment of biosensors, and we can literally see at the upper part of the picture, and there's a row of flower pots with flower of varying colors from left to right. And at the very right, there's also a pot of flower that contains unknown amount of soil, which is weight to be determined. And in the lower part of the picture, there is, it shows the changes of 3 potted flower over time, and while only one of them grew larger than before.
Okay, so I'll be going over the scientific processes in the photo. So the top half shows a shift in color values representing a colorimetric sensor, which we did talk about a little bit earlier. So the response here is the different values or the colors. And basically it takes an input from the external environment, which is basically the water, and it affects the color. And this part also represents a calibration curve because the X value, which is the water, is affecting the Y value, which is the color. And we are trying to find the unknown, which is the X amount of water with the Y value of color. So that's a lot. So let me just go over this again. So the calibration curve is the color is going to be your Y value, so the color of the flower. The water is your X value, and on the very end of it, after you look at your calibration curve, you're trying to find out how much water you have
for the last flower. And then you have your bottom section, which is showing how enzymes speed up reactions. So essentially, you have 2 flowers, which are both plant type A, and then you have 1 flower, which is a plant type B. And 3 days later, your plant type A, your first flower is growing a lot versus your second flower of plant type A grows a little, and then your final flower is not growing at all. And so the fertilizer is representing an enzyme. So the enzyme in plant A speeds up the reaction rate. So after 3 days, it grows really big. And then your second one doesn't have any fertilizer, showing how it grew without the enzyme, but not as fast. And then your final one with the plant type B, it has fertilizer, but it didn't grow because enzymes only speed up certain reactions. And yeah.
Okay, so the context of this lab was that we basically were working with biosensors and a colorimetric scale. So when we did this with our beads, they turned pink when exposed to different chemicals. In this sense, they use flowers with water in the color. And one of the limitations to this picture is that we're not really sure what that question mark means. I'm sure when you see that, you're like, why is there a question mark? What does it do in this sense? So a calibration curve is basically using something that we know to find out something that we don't know. And in this sense, we don't know how much water is in this tank. So I feel like if the artist included something like a person trying to find out how much water there is, maybe like a comparison of between, or like a little more steps rather than just a flower there with a question mark, I feel like it can make it a lot more clear that we're trying to find how much water is in that bucket with something that we know. On the bottom here, what we didn't include is that the fertilizer, an enzyme, which is represented through the fertilizer, an enzyme is very specific to what works and what doesn't work. Like, and some enzymes, when you put it in something, it doesn't work because of the biological aspect of it. So I guess without context, it's kind of hard to understand why the fertilizer worked for this plant, but not plant B. And realistically, plants don't grow that fast in 3 days with this kind of fertilizer. All right, thank you.
Thank you.
Okay, so I noticed you guys mentioned biosensors, and so did the other group that was kind of talking about the analogy with a colorimetric sensor. But do you think you guys could go more in depth about what biosensors are for the parents here?
Yeah, sure. Okay, a biosensor is basically something that uses their biological aspects. It's built of something natural or biological, and then it senses other things that are biological. And it basically takes a signal, and then it goes through a transduction, and then gives a response. It's like a machine. So you put something in, and it gives you an output. But this, the artist did not include it whatsoever. I feel like if we wanted to include it, we could say that maybe inside the petal, parts of the petal, or like if you look into the petal, maybe like the molecules are changing color in there. That way you can give like a clear transduction, like the process to get a response, given a signal, which is the water. But in this case, the biosensor part was not very clear with this design.
So you did mention that the bottom is talking about the enzymes, and I agree. I think it actually gets at specificity of enzymatic reactions really well, in the sense that plant type B doesn't grow, so that fertilizer is not designed for that type of plant. And there are different fertilizers for different types of plants. So in the real experiment that you guys did, how was enzyme specificity important, and what did you do in the real lab to understand the specificity of the enzyme?
In our real lab, we worked with beads that detect glucose, and then we put them in different liquids. Some of these liquids had sugar, which is glucose, and some of these were like apple juice, orange juice, and you would think that, and then when you put the beads into these liquids, like with sugar or with orange juice, with energy drinks, it would turn pink if it detects glucose or sugar. However, we realized that when we put in these beads, they did not turn pink when we put them in orange juice or apple juice, I believe. And that was because the enzymes in these beads, it detected, they only detect glucose and not fructose, which is in juice. So that's why our beads did not turn pink. And that's how it's represented in this picture.
Hey, afternoon, folks. Nice presentation. I have a question about these water plants that you have on the top. For your calibration curve, if you have more data, more plants, does it affect the accuracy of the curve? If you, like, for instance, had only 2 plants, and then you could calculate the unknown versus having 5 plants and doing some unknown, experiments. Thank you.
Yeah, I think it definitely affects your accuracy and precision, because if you have more known values, it's better for your unknown value to exactly pinpoint the exact color of your known values. So in this case, if you had more values of your flowers, right, and then you had a flower, you'd be more accurate to compare it with the right exact color and find the amount of water, versus just 2 plants and then having a 3rd plant that doesn't have a very similar color to either. It won't work as well.
Okay, and then who's our artist?
All right. I think you guys did a great job with kind of explaining this, and you guys kind of hit everything kind of on the head. And good job.
Thank you.
Oh, my name's Maddie, by the way.
All right, thank you. Group 9, Group 9.
Good job, team.
Group 9. Nobody's moving.
All right, hello everybody. Good afternoon. I'm Milo Levin. I'm a rising junior at Los Altos High School down in the Bay, and today we're going to be presenting this analogy about photolithography.
Hello, I am Leela Trussell. I am from Torrey Pines High School in San Diego.
My name is Alexander Slikos. I'm a rising senior from Clovis North in Fresno.
Okay, perfect. So first we'll be starting with what we actually see in the image. So first you see there's a person who is going to get a tattoo in a tattoo parlor. They're prepping his arm, shaving with a razor, making sure it's all clean, a proper surface to then start the process of getting a tattoo. They put the stencil, draw the tattoo, wait 15 minutes. Then you see them getting the actual tattoo, cleaning it off. And then after you get a tattoo, it's very red. They put on lotion, and then he leaves. And then for the bottom portion.
And the bottom portion it's just demonstrating that a thicker needle it just leaves a unclear, it's a not clear resolution picture, and in the drawer it shows that he has shorter and thinner needles, which he could use, and step 11 says that depending on the skin, it's easier to tattoo on, and it's easier for simple designs as well.
Perfect. And then for explaining the scientific of what is intended with this analogy is that when you're walking into the tattoo parlor, that's like walking into the clean lab, and you are going into a totally sterile environment. So it's kind of showing he's getting ready to he's going in the proper environment to get the tattoo. It's going to be safe. He's going to not get infected. Then if you look on image number 2, this shows him being razored off. He's cleaning his skin, which is representing the photoresistance in our experiment when we coated the layer. And in this analogy, I believe that the hair represents the photoresistance, and then in step number 3, we see the mask, which is the stencil, and then the copper would be the skin, although later we will get into the limitation, which is the lack of clarity on where the substance is. Then if you see on image number 4, you see the weighting, which is the exposure. In the actual lab, it was exposing to the sunlight, but as it's an analogy, this shows that you basically just wait for the tattoo to develop, making sure that the ink is dry, to then be able to actually develop the tattoo, which is step number 5, with the tattoo gun, which is to make sure that it will stay inside the copper. Then on number 6, you see that he cleans it with a wipe, which is representing the etching and taking off to show your design. And then number 7 shows the developing of, after you etch, just cleaning it off, making sure that none of the acid is still remaining on the board. And then number 8 is showing him leaving the tattoo parlor with a new tattoo.
So for number 9, it's just demonstrating, the analogy is demonstrating that you attain a lower resolution photolithography, like the printing design, because the wavelength is too large, seeing that the needle's too thick. So it's gonna be a blotchy resolution. But it shows that the printing design can be more clear and defined. If he lowers the wavelength, it makes the needle shorter and thinner, and that'll make the resolution higher. For number 11, it's so much easier tattooing on soft skin. It's the nature of the material is a factor of resistance. So you can't conduct through wood, but through metal you can conduct a lot easier. So the resistance is much less for metal versus wood. And simple designs are quicker and simpler.
And then, sorry, I have to cut you off.
I got 20 seconds for these limitations. So I'm going to kind of simplify it down. As we can see through these first images, it's kind of an additive process. You're adding a stencil and you're kind of drawing over it, adding what would have been copper in the real experiment. But what we really did was kind of a removal process. We used acid to remove any material that was not protected by the photoresist, the light-sensitive material. But there's my time, unfortunately.
Sorry.
All right. And to give another specific example, as we can see with the razor, they're removing hair. But what we actually did is we added the photoresist, a light-sensitive material that reacted to the light with the cover of the mask to create a shape. And the skin, while it does show, it is in a sense light sensitive, it's not in the way that you make a protective mask to prevent it from being removed, like we did in the experiment.
So on panel 7, do we know why it just says here's some lotion? What's the purpose of the lotion in the sense of kind of translating to photolithography?
Right, so it's a little unclear in this analogy, but I believe that the intent was to show that it's stripping, kind of just cleaning. If to improve this analogy, it might have been more accurate to state that it was more of a cleansing, just to wash off the ink more or less. But as my group and I talked about it, it seemed that it would line up most logically to have these steps in this order, and it ended up that the strip would work out there. So yeah, hopefully that helped.
All right, correct me if I'm wrong, but did you say that the copper was the skin of the person?
It's a little unclear because the copper and the substance, the two layers, are not very well shown. So in the experiment in the lab, the etching would have been actually at the copper, which isn't exact, which there's a different process happening here. So I would say, I'm gonna correct myself and I'm gonna go with that the substance is the skin.
All right, and then can you clarify?
Substrate.
Yep, yeah. And then can you clarify what the word etching means, for everybody here?
Yes, so, oh, go ahead.
It's using acid to cut into the metallic surface.
I mean, to add on to that, there is a part of the metallic surface that is protected by the photoresist, and any part that is not protected by that will be removed during the etching process. So, yeah, and this, it doesn't really show that as well because it's adding it on, but it's kind of like a protective layer to prevent, and everything else gets removed.
So I just wanted to clarify a couple things that I think I heard you guys say when you were doing your explanation. So you said in the lab that you were using sunlight to develop your materials, but I don't think that's quite correct. And you did point out something else that is correct, which is that the size of the needle is an analogy to the wavelength. So what wavelength did you actually use in the lab? And then, like, when you went to the clean room, for example, why was the ambient light in the clean room yellow?
So we used UV light, not sunlight. It's a more powerful wavelength. And we used, in the clean room, there was not white light, because white light is all wavelengths of light. And that would be really damaging to this very photosensitive material. So another way to think of it would be like thinking of developing a photo. I mean, if you've ever seen the older process used in red light, in darker rooms, and this is to prevent the really photosensitive material from being affected. I mean, otherwise you'll have like blotches everywhere, and you won't have the clean, sharp image that we really need to develop these really small, precise nano, because just any little photon that hits in the wrong place, maybe a few, might really mess it up.
Okay, those are actually very good answers. So I want to ask one quick question. We're running out of time. So many things I could ask. Okay, the shaving. So the shaving is a step that is done, but you didn't do it. So what is the shaving actually?
Oh, it's removing the dust before entering the lab and just making sure that you're fully cleansed. Is one way of looking at it, is cleaning off.
Right. So it would actually, so normally when you do photolithography, before you put down the photoresist, you have to super clean your substrate, and then you put down the photoresist over it. But we handed you something that had photoresist already deposited on the metal. So you didn't do that step. But it is a part of the real process. So you guys are being really literal here. And the big picture process and your experiences are different. And when the analogy doesn't capture your experience, find a different experience you learned about and try to map the analogy onto that one. Because there is a lot of science here. So for example, one more comment. You guys very correctly said that you guys did a subtractive process where you etched. And by the way, etching doesn't have to be acid. Any chemical that takes stuff away is etching. So you did a subtractive process, but this is an additive process where you're adding color on top. But there actually are kinds of lithography that do additive process. So where you make a
negative or positive masks.
Negative or positive. And so you can, say what we did was this, but what this picture is describing would be a better analogy to that. And those are all great. It's just an excuse to discuss science.
Perfect.
Okay, good job.
All right, and our artist, please.
I know there was a question there, but we are out of time. You'll never get to
So like my name is Lawrence. Yeah, I'd say that they did pretty well. Yeah.
All right,
Thank
short
you all
and
so much.
sweet. Thank you. Group 10, come on up. All right, so again, just some context. These are our other set of volunteers that volunteered to draw a drawing during lunch. And so they drew the first picture that we saw with group 5, and now they're going to present on the second group's drawing.
All right. Hi, everyone. Yeah, as she said, this product is an incredible feat done in a very short period of time. So let's begin. I'm Varchis.
I'm Sachi.
I'm Ouyang Ruochen.
All right, let's begin. I love pizza. All right. So the other day, I found out I had a leftover slice in the fridge. Great. I was going to warm it up. But with what? An oven, an air fryer, or a microwave? I couldn't pick. There were pros and cons to each one, so what did I do? I thought of the supercapacitor experiment that we did earlier today here at UCLA. Now, let me give you a short summary of what our end product was. Electricity from a power outlet flowed to a circuit board, which we created. It was then transferred and stored in a capacitor. Now, we had an LED light, so when we turned on the circuit, electricity flowed from the capacitor to the LED light, lighting it up. Specifically, in this experiment, we focused on the pros and cons of batteries, supercapacitors, and capacitors. So that's something we'll analyze later. Now, let's look at the actual drawing. There's a person here who wants to heat something up, just like me. 3 options: oven, air fryer, microwave. As they try all of them, there are some reviews they leave. For a microwave, it heats up really fast, as we know, but no one likes microwave pizza. It's raw. The oven is the other way around. I'm not waiting 30 minutes for my pizza to heat up, but it will taste good. And here we see a blown up image of an air fryer, which we will analyze later. Now we'll go into the explanation of what the analogy means.
Okay, so in the first step, as he said, the person is wanting to cook chicken, and he's trying to figure out the best way to cook it. And then in the second part, the oven, air fryer, and microwave are analogies for the battery, which is the oven, the capacitor, which is the microwave, and then the supercapacitor, which is the air fryer. And the oven's the battery because it takes the longest time to cook, and it's a slower process, and it does cook it well, but it just takes a longer time. And then the microwave, which is the capacitor, cooks it in the shortest amount of time, but it's still raw. And then the air fryer cooks it kind of in the middle amount of time, but it cooks it perfectly. And yeah, so the supercapacitor is the best option. And then in the fourth part, it kind of is like a diagram of the air fryer, aka supercapacitor. And it shows the heat waves, which is what's cooking the chicken. And in the experiment we did, it's what we used our supercapacitor to light up a little like red light. And it's, I guess, like the energy to cook it. And then it's here. It's showing how a supercapacitor has a greater surface area, which is what makes it a better option to like power stuff. So it says more space in the microwave. And then here it's also talking about the greater surface area by showing that when you like open, so there's like incisions in the chicken, and then when you like open it up, it makes it cook faster. And that's also related to up here there's a drumstick, but down here there's a chicken breast and a drumstick because there's a bone in it, takes longer to cook than a chicken breast would. So yeah.
Okay, there are some limitations in the analogy, and the first one is that, in real life, the oven, air fryer, and microwave are always being charged, but for the battery and capacitors, they can frequently replenish their energy. And the second limitation is that some people for people who don't know much about cooking, they may not get a concept. For example, they may not know the purpose of the incisions. Yeah.
All right. Thank you, and we're happy to answer any questions you might have. All right, so any questions?
I think in the lab you guys learned about specific energy and specific power. Oh. Yeah. Could you explain that the 3 different ways of cooking in terms of the terminologies that you learned?
Yeah, sure. So this is something we addressed in our own picture as well, the one with the water. So a microwave is essentially the first thing in ours, which was the little toy bucket with the hose. So this is essentially, this is it has a short power supply and it drains really quickly. It's called a capacitor, which is the electrons are stored on the surface, essentially like a petri dish. So everything escapes really quickly, and there's a lot of energy going at once, but not for a long duration of time. The air fryer is the medium, which is the supercapacitor, and we like this because it was a balance of the two. It took longer, but it was also baked well. And the oven is the battery, which can store a lot of energy, but it takes a lot of time to release it. It's quite slow. So those are the relationships in the analogy.
Yeah, and just to add on, I think one limitation we kind of were thinking about was the oven, air fryer, and microwave all have like unlimited supplies of energy, I guess, because you just plug it into a wall. Whereas a battery, one of the big differences between a capacitor and a battery is a capacitor runs out of energy faster than a battery would. Yeah, and they kind of all will have the same kind of battery life, I guess. Yeah.
Okay, so I want to just follow up on that. So what you said is correct. These are heating devices, not energy storage devices. And so they're attached to the wall, so they have infinite energy that they can draw, whereas an energy storage device has a capacity. But there's still an analogy to power density. So what was power density?
So essentially here, the oven, it takes, essentially in the microwave, it's a smaller space, but all the energy comes at once. So because it's smaller, everything, like essentially it's released at an extremely dense rate, but quickly.
But so I just want you to get, there's an analogy to power density. So power density in a normal sense is, well, how would you define power density? I could define it, but I want you guys to just define power density, just that small thing.
I would say it's the average amount of power released in a certain period of time.
It's energy per time.
Right.
So what flavor of energy are we talking about in these cooking devices? Just one specific flavor of energy.
Heat.
Heating. So the analogy to power density is heating per time. So then could you comment again? And particularly amount of heating and how fast it's delivered. Because there's actually quite a nice analogy in these three.
You could go ahead.
All right, so yeah, like we said, answering that, the oven takes they all heat the same amount over time. Your pizza will be the same temperature when it's done, but the oven takes the longest period of time. So the amount of heating per time is the least. This is why we thought it was the battery, because the energy output is very slow.
So in terms of power, how would you describe it? Not in terms of just energy, but in terms of power.
Okay, I'll start with the microwave, but the microwave I think would have the most power because it's the shortest amount of time. But
yeah, so we're doing an analogy, and so it's the most heating per time. So that's an analogy to highest power.
Mm-hmm. And yeah, the microwave would have the highest power, and then I think then the oven would have the least amount of power because it takes the longest time.
Yeah, so I would make the analogy, so normally in batteries we mass normalize it, so energy per mass per time, but in this case I would area normalize it. So I would say heating per area per time. And so there's a big area in an oven, and so although you're dumping a lot of energy, and any one piece of the oven, you're not heating it that hot. The air fryer basically is just a spatially concentrated oven, so that you're dumping more heat faster, but you're heating a littler area. And so it's really actually quite a good analogy in that score to the battery supercapacitor and parallel plate capacitor.
All right, and then our artists.
Any comments?
Yeah, overall the presentation was really good. It described our thought process really well, especially it was complemented by Dr. Tolbert's, questions. So yeah, good job.
I'd just like to apologize just a little bit because we were like, well, like you guys, we didn't really have enough time to
Yeah,
like
no worries,
fully
no
make
worries.
it, comprehensible. But props to you guys for like understanding our message. Great job. Also, like the clock thing. Just a little note. We didn't mean to make it like literal. It was just to show like the difference in time. So they weren't actually putting something in the microwave for like 15 minutes or anything like that. But yeah, great job.
All right, thank you.
Thank you. All right, group 11.
Okay, what group 11 comes up, let me just say, nobody ever needs to apologize. The point of the discussions is that you learn about the science by discussing where the analogy holds and doesn't hold, and thinking about what is the meaning of power density and energy density. So these are all great pictures. Never apologize. Just, help facilitate the discussion.
I'm Gotham.
I'm Zoe.
I'm Sophia.
So in this picture, it took inspiration from the biosensor experiment we did on Wednesday, I'm pretty sure. So in that experiment, we had an enzyme and we put it into a nanoporous bead, and we placed that bead inside of many different liquids, and the enzyme is supposed to trace how much glucose is in these liquids. So based on the amount of glucose, it would turn either like a bright pink or a light pink, or if there was no glucose, no color at all. So in this picture, literally what we see is there's a man dishwashing, or he's washing dishes, and if we take the top path, he has a dish with like some amount of soap. So then he thinks of like 4 different types of dishes with different amount of soaps, and then from that he realizes what type of sponge and how much water he needs to use when washing. And then if we look at the bottom path, we see that instead of just doing all that work, he decides to just get a washing machine to speed up the whole process, and he's happier.
And now is the time to talk about the scientific concept. So the first concept is colorimetric sensor and calibration curve. So a colorimetric sensor is a sensor that output the response with different colors, and a calibration curve is relating the response with the signal, so that by relating and comparing the color with the calibration curve, scientists can know like what the colors represent specifically. And in this graph, the man can know how soapy the sponge is by comparing it with 4 pictures on the top right corner. And the second concept in the graph is enzyme, which is a catalyst that speeds up chemical reactions without being exhausted. And in this picture, the enzyme should be the dishwasher, which speed up the dishwashing process.
And so this is a great analogy, but there's still some limitations. So first, in real life, people actually don't need to look at how much soap there is to decide how they need to wash these plates. And for the sensor, it works based on 3 steps: signaling, transduction, and response. So we believe that this analogy shows the signaling and response very well. However, it doesn't show the process of transduction very clearly. And for these 4 plates, which represent the calibration curve, they just show how these 4 plate looks like, instead of showing the differences between their colors, which is a property of the colorimetric sensors. And this analogy takes a dishwasher as an enzyme, which is a great idea. However, this enzyme is not involved in this sensory process. And that's all.
So just a super quick comment. We only have one more, but I'm still just giving you conceptual things. It does not matter if the thing that is drawn actually happens in real life. The things you're supposed to be talking about are, how does it capture the science. And so like when you said the transduction is not in here, that was exactly perfect. When you say people don't look at plates and decide how much soap to use, well, I can tell you that when I look at plates, I do decide how much soap to use. So those are not the things that you want to just do the things that relate to the science.
So speaking of transduction, this is a good transition for me. So what was the actual transduction that was happening in your experiment? Because a lot of you have talked very well about the fact that you used the enzymes and it changed color, but like what was actually happening that eventually did cause that color change? Can you describe that science in the experiment a little bit more?
You mean in the like sugar detecting one? Okay. It's basically sucrose combining with oxygen and then combining with H2O2 to form a new product, and that product has color, and based on how they react, the color will change.
So what was the enzyme doing?
It speed up the combining process.
But so what was the enzyme? Like what was the first enzyme, the main enzyme you were using? What was it called? Do you remember?
So you actually had, in your biosensors, you had two signal transduction response reactions happening in your biosensor. So Dr. Blake is asking about the first one. Your signal that you were looking for was glucose. What transduced the glucose into then the first response? So maybe what was the first response that you generated? It was not the pink color in the first flow.
Pretty sure it was H2O2.
Correct, hydrogen peroxide. So you went from glucose, something transduced that glucose into your hydrogen peroxide. What was that one?
What was the name of the enzyme? And it does have the word glucose in it. Glucose what? Do you remember?
Anybody in the audience? Enzymes are great because they usually tell you what it does, and then it adds an A's at the end of it to tell you it's an enzyme. Yeah. Correct. The first enzyme was glucose oxidase, right? So we took the glucose and we took a part out of it to get out that H2O2. Okay, then what was the second set of signal transduction response in your biosensor? Well, what was the response?
The pink color.
The pink color, right? And then what were you taking from your first thing that was the response?
The H2O2.
Right, so you had H2O2 as your signal now, then another enzyme that transduced that into our pink color. So what was that second enzyme, and what was it doing?
What's another way of saying like H2O2? What is that?
Hydrogen peroxide.
Correct. So the enzyme has...
It's like that and an ace. What approximately was that enzyme?
Do we want to phone a friend? Or ask the audience? What are our different... Who wants to be a millionaire? Yes, George. So it was actually horseradish peroxidase. So it's HRP. But yes, the peroxidase part was the key part. So... And it came from horseradish. Right. Okay. Did we want to so just to could you summarize that then for us?
Make sure you say what you just said, like together.
So like we had the
Glucose.
The glucose, and then it had the transduction step of the glucose oxidase, and then it produced hydrogen peroxide. And then the new signal was hydrogen peroxide, and then the transduction was the horseradish peroxidase, and then the final response was the pink color.
Awesome. Great. Okay, and then our artist for this one.
My name's Antonio, and I'd like to say that you guys did pretty good, except for the fact that
I will defend my stance on putting more soap if a plate is more dirty.
All right, thank you. Okay, our last group, group 12.
Also, just you guys did a good job of actually saying this was the real science, and then this was the picture. And so, particularly good job on that.
So my name's Eric.
My name is Anurag.
My name's Ashi, and today we're going to be talking about the photolithography experiment. So basically, in the experiment, we fabricated a circuit board through photolithography and tested the resistance in the fabricated circuit by using a multimeter. So in the context of this drawing, basically, panel 1 is a baker who's making batter. And in context to the experiment, it's kind of similar to how we were coating the substrate with photoresistance, because they both are basically like the introductory step. And then in panel 2, we showed the baker, well, we interpreted it as the baker kind of pouring in the batter into a pan, making it similar to like aligning the material, because in a way, like when you're pouring the batter, you have to spread it out and make sure it's all uniform and even. And then in panel 3, it shows the cake being baked in the oven, which is similar to in the experiment how we would expose the photoresistance, except in this, the cake's in an oven, but during the experiment, we were flashing a light under the box. And then in panel 4, we're showing the cake shape being cut out, which is representing the development of the photoresistance, and the remaining parts being covered by the mask. And then in panel 5, we're showing the cake being iced, which is similar to, in the experiment, the etching process, because when icing a cake, you tend to start off with a really messy process, but the more you ice it, the more refined it gets, basically. And panel 6 is adding details to the cake, which is technically representing the stripping process, but in this case, it's more like refining the cake and adding detail.
All right, so moving on to panel 7. So in this case, it's talking about the feature size. So you see the real menu here. It only shows 3 menu items, but if you look at the menu on the phone, it shows like 50 plus more. So it's trying to show that it's able to fit more stuff into the same space, but also make it more complex. So panel A here shows that each materials have different resistivity. So he's cooking the egg with the cake with the egg, which takes less time, and without the egg, it takes longer. So it's trying to say like different materials have different resistivity, and it's also showing the thin and thick wires here with the more cake and less cake. So yeah, it's trying to say that the thin cake has more resistivity, and the bigger cake has less resistivity. And moving on to panel 9, yeah. So in this is showing the sequential and parallel process. So over on the left, it's trying to say that they're packaging the cake one by one. And on the right, they're packaging all 3 of the cake together. And moving on to panel 10, which is basically Moore's law. So it means the amount of transistors that can fit into the same space doubles every 2 years. So it's trying to say that his bakery makes double the money every 2 years. So that's how that translates. The next panel is talking about transistors. So a transistor is basically a semiconductor device that amplifies or acts as an electric switch to control the flow of the current. So the guy yelling stop there is like the transistor. He's controlling the flow. He's asking it to be stopped. Yeah. And panel 12, which is representing of the clean room. So yeah, so in the clean room, you don't want any dust in there. I mean, as less dust as possible. And in the bakery, you don't want any dirt in there as well, because that would ruin the cake. Yeah.
Here at the bottom, you can see 2 different cakes with 2 different pipette sizes. So the one on the left has smaller, so it can be more precise. And the one on the right is bigger. So this kind of relates to like a scanning electron microscope on the left compared to a light microscope on the right. And the difference between these two is that the light microscope on the right uses a wavelength that is pretty high because it's visible light. And on the left, it uses electrons, so you can see much smaller things. And now I'm going to address some of the limitations of this. And firstly, I'd like to address the fact that the artist did a really great job and answered every single question that we were supposed to address in the image. And the first thing I'm going to say is at the top, it's a little unclear, like the steps like masking and adding the photoresist. And where it's baked, there's 3 cylinders baked. So after that, the exposure step, the 3 cakes are stacked on top of each other and cut out. So I think in our real experiment, the etching that we did was, it cut out each layer separately. So maybe if each layer was being cut out in a different step, it would be more clear. And even in the detailing step, that is supposed to represent stripping the photoresist, which in this case, it kind of adds onto the cake rather than making it, removing from it. And the final thing is where it says cooking time, there is 2 cakes, one smaller and one bigger on the right. This is supposed to represent resistivity. So generally, a thinner wire would mean there's more resistivity. So in this case, the smaller cake would take longer to cook, so those would be switched. Yeah.
So I know you guys mentioned resistivity and resistance, but I'm not sure if the analogy include, but how would you describe the importance of resistivity in terms of when we're calculating and calculating the resistance, and what does it depend on?
So the resistivity is completely dependent on what is actually the substance. So as you can see in the analogy, it says with egg, it takes 10 minutes to cook. So you could say there's less resistivity there. And then without an egg, it takes 15 minutes to cook. So that could mean there's more resistivity.
I want to ask about the 4th row down. So the process, parallel, sequential, and Moore's law. So nice job explaining it. Can you describe, though, a little bit more how that works for real-life semiconductor manufacturing? Like, how is it sequential versus parallel? And then how does that then relate to the ability that happens with Moore's law?
So I think the sequential is like you're taking it like one by ones, and the parallel is like you're using them all together at the same time. And for Moore's law, it's basically in our daily computers and phones and stuff. So we're trying to pack more stuff into a compact space. So so we're just, but we also at the same time we want to make our computers more powerful. So that's why the transistors are there to if you make the transistors smaller and pack them to a smaller space, they could they could be more powerful and just and be more compact in general. Yeah.
But can you clarify, what do you mean by, what's 1 by 1 versus what is all together? Are the lithography steps 1 by 1 versus all together, or what part of it changes to be 1 by 1, or what part of it changes to be all together instead of 1 by 1? Can you clarify that a bit, based on maybe what you saw in the clean room, when you looked at real wafers being manufactured?
So in the clean room, the wafers are being transported from one spot to another, 1 by 1. While if it was be parallel, they will be all transported at the same time.
Well, wait a second. What were what was being made on the wafers? Just vaguely, what's the term for what you usually make? What's the heart of your phone or your computer?
Oh,
a chip.
The chips.
Integrated chip. Okay. How big were the wafers you saw?
We saw all kinds of sizes, but generally this big.
How big were the biggest ones? Yeah, that big. Okay. How big is the chip in your phone?
Really, really small.
It's like, yeah, about maybe a centimeter across. So what was on that big wafer?
No, it's a lot of different chips.
It's a whole bunch of chips, and then they dice it up. There's wafer dicers, and they cut it up into little tiny chips. So what was parallel? If you do a process on one wafer, is that 1 by 1 or parallel?
That would be parallel.
That's parallel, because there are a whole bunch of chips all over on that. Okay, so I have a philosophical question, because you are group 12. So everybody has had, you guys commented that it's hard to make these analogies because you guys did a subtractive process where you etched away something. And most of the real life examples that you come up with are additive processes where you deposit things like layers of cakes or handicap signs on streets. Why is it that in real life, in the macro scale, we usually do additive processes, and in lithography, we often do subtractive processes?
At the large scale, like we're like, let's say on like ground level, we start with nothing, so it's easy for us to build up from there rather than like going backwards.
And if you did a subtractive process, what would that involve? Like, use the cake as an analogy.
Maybe you like make a really big cake and then go down from there, like cut it up and design it like that.
And why don't you do that?
It wastes materials.
It wastes a lot of materials. Why do you do it on the chip scale?
It's really small.
It's really small, so you're not wasting much material. And in fact, all the money is in just depositing it. It's not in the amount of stuff. The layer is so thin that it's not a significant amount of material, and it is easier to deposit a big flat layer and then take some away. And because it's a little amount of material, it doesn't matter. And that's why everybody's having so much trouble making analogies to a subtractive process, because we don't do them in real life too much, in macroscopic life, because they are wasteful. But it's interesting to think about the fact that you can be wasteful at the nanoscale, because it hardly matters how much material you're wasting. It's all just about all the energy and cost is in the machines and the vacuum and the energy to do the deposition, not the amount of material itself. Yeah, good job.
All right, and our last artist, please.
My name is Joseph, and you did great on the analogy. I couldn't say it better.
Right. Thank you. Okay, so I'm going to just do a few little closing remarks. So first of all, thank you, students, and great job. Secondly is that while we only had you guys for 5 days, we see you as our students forever. And so we want to help you succeed. So we'd love for you to stay in touch with us. Let us know what it is your plans are, college, university, pursuing a PhD, an MD. One of our speakers talked about an MD, PhD. I do not recommend, but if you want to do it, we want to hear about it. If you're starting a business, earlier I mentioned our CNSI Nanovation competition. Those applications open in December and January. And again, that's nanoscience and entrepreneurship, if anyone is interested. And then we have other summer sessions courses. These courses open in February 15th, and they fill really fast. But we have our nanoscale microscopy class. That is a 1-week program where students get to use some of the instruments in our technology center. Applications of nanoscience, that's basically that nanovation competition, but condensed down to 2 weeks. And then you guys are in Nanoscience Lab here. And then also we write letters of recommendation. So I know some of you are just entering your junior year. Some of you are entering your senior year. So even if a year from now or 2 years from now you need a letter from us, you just shoot us an email and we will get that process started for you. Lastly, I want you guys to take a moment to reflect. Remember our skills in life. One of them is reflection and introspection. So students, I want you to just think about what you knew about science or nanoscience before you started this course. What did you learn over this past week about science, research, science communication, teamwork, and about yourselves? Okay, so just take a moment and appreciate all that you guys did, all the hard work that you put in, and be proud of yourself for all that you did this week. And then last but not least, we need to thank our parents, who are amazing. We just want to thank you, parents, for giving your students this opportunity. We know it comes at a literal cost of money, and you are really, truly investing that money in your students' education, and we really appreciate that. Sarah talked about how her kids have done this program. My parents invested in my education so that I'm where I am, and so we thank you for doing this and giving your students this opportunity. So again, one more time, we really need to thank our parents. You want to say something, Professor Tolbert?
Yeah, so I don't know if we have already thanked the any of the grad student mentors who are here and the undergrad mentors who were the RAs. There's a word for it, RAs. So a whole lot of people. The only way that we can put on a program of this magnitude is to have a lot of people who are really capable as teachers all pitching in at once. And so I would like to just take a moment to thank, they're not all here, but those who are here will pass on. So let us thank all of our mentors. There's two people that need some special thanks. You have heard a lot of questions from Dr. Rita Blake and from Dr. Shailene Tanimoto, and they are your amazing CNSI staff leads here who have been running this entire thing. So please let us give a huge, huge round of applause to these two folks. I have to give an extra applause because, I mean, it is because you guys are so amazing that I get to be a part of this and at the same time doing all of the other 50,000 things that I'm doing with my life and knowing that everything is running super awesomely. And then I just want to say a couple things to the students before we go, which is when we started this course, I said, you're going to look at me and your eyes are going to roll and you're going to say, why do I have to draw pictures as my homework assignment? I'm too old for art projects. But I hope that in the course of this, you have realized that conveying scientific concepts graphically is actually really at the core of communicating science. I want to remind you that as you go out into the world, whether you become a scientist or you don't become a scientist, you need to be part of the solution for our country to be scientifically literate. That means for people to generally understand what is reality, what can science do, what it can't do. And communicating science to non-scientists is at the core of that. And so I am charging you for the rest of your life to teach people the things you understand and to help make a country where we can have logical discussions based on facts and figure out what the best course of action is. Not always easy, but be a part of that process. So thank you for doing this. The last thing I want to say this in front of the parents. I said this at the beginning. I want to remind you that this is an actual UCLA course, and I will assign you I will assign all of you a grade. And you will have an actual UCLA transcript that has this course on it. And you can email or go to the UCLA registrar site and you can have them send your official UCLA transcript to your high school. Your high school will attach it to your high school transcript, and they will send it out to colleges. If your high school won't do that, you can also directly send it from the UCLA site to colleges that you apply to. So please take advantage of the fact that you have a real course on your transcript and let colleges know about that. Last week when I was talking to parents, they're like, my kid never told me that. So now I'm telling all of you, so you can help do it. And then I just want to end by thanking everyone for being involved. This is our last day of our last course of a long summer of nanoscience. And so thank you all, and let's go have a little celebration.
Yes. Okay, students, we want to get some feedback, so if you all, I will send this via email as well later, but if you guys could fill out this survey. We'd also like to take a class photo. We'll do that as well. And if you are staying in the dorms and you are leaving tonight, please let our RAs know, or else they will blow up your phone tonight at curfew check time. All right, so students, please meet outside the building under the California Nanosystems Institute sign so we can take a class photo, please.